Okay, so today's speaker is Dr. Rixin Li. Rixin is from China. He did an undergrad in Peking University, and he received a PhD from University of Arizona in our department last summer with Andrew Uden. And his thesis was on planetesimal formation and dust evolution planetary disk. And from this fall, he joined the Cornell Center for Astrophysics and Planetary Science and working with Dong Lai. So here we welcome Rixin again to Origin Seminar. We miss you. Floor is yours.
Okay. Yeah, thanks, Serena, for the warm introduction. Yeah, I'm very happy to have this opportunity to come back virtually to give a talk. Yeah, I would love to really go back. Okay, today I'm going to talk about the thresholds for planetesimal formation by the streaming instability, as the title suggested. Okay, so in the current theoretical understanding, planet formation takes place in protoplanetary disks through the following stages. The critical first step is the accumulation of dust and ice particles into planetesimals. And the rest three stages are the so-called co-accretion model of planet formation, where planetary cores built upon planetesimals further accrete disk materials and become larger. The final planetary architecture also depends on the planet migration and the scattering. But in order to build cores, we need to first form planetesimals from dust. And to give you a clear definition of planetesimals, they are 1 to 1,000 kilometer sized building blocks of planets, and the materials inside planetesimals are not held together by chemical forces, but by their self-gravity. A fun fact is that they are the least massive objects among all the gravitational bound bodies in the universe. Although we cannot directly observe the formation processes of planetesimals in protoplanetary disks, studying planetesimal formation helps bridge the observables, especially in recent exciting new discoveries. Disk observations provide key context for forming environment of planetesimals. With ALMA and extreme AL systems, we are now able to resolve nearby protoplanetary disks to the scale of a few AUs. And this picture from a D-Sharp team shows the dust continuum in millimeter wavelengths, revealed various disk substructures and how dust particles distribute in disks. And in addition, the observations of planetesimal remnants from the early solar system and the architecture of the exoplanetary system provide rich clues to constrain the outcomes of planetesimal formation models. And in particular, the New Horizon mission offered the first up-close look at the outer solar system object, the aerodynamically. As the critical first step in planet formation, building planetesimals out of dust particles is not an easy task. This picture shows the key scales of planetesimal formation, with long axis in the middle denoting the particle sizes for more than 10 orders of magnitude. People often also use dimensionless stopping time, tau s, or sometimes Stokes number, to describe the particle size. It indicates how fast a dust particle responds to the ambient gas, and most of the time, it scales with size linearly. And in typical disks, a stopping time of 1 often indicate centimeter to decimeter particles. Broadly speaking, there are two types of dust growth, the bottom-up growth and the top-down growth. And for the first one, particles grow by collisional coagulation. And when bottom-up growth reaches its limit, top-down growth mechanisms are required to concentrate solids to form larger objects. An important question is how far can such staking growth go? What initial conditions does bottom-up growth provide to the top-down growth? So there are two barriers put a limit on the bottom-up growth in dust evolution models, as shown in this famous example. This picture shows the dust distribution as a function of disk radius and the dust size in a global simulation of a typical disk. The first barrier is the radial drift barrier. In a smooth protoplanetary disk, gas orbits at a sub-Keplerian speed due to the radially outward pressure support. But dust particles don't have such pressure support. They lose angular momentum to the surrounding slower gas and drift inward. And more importantly, they drift faster before they can grow to substantial size that are less affected by the gas, as demonstrated by the dashed curve here. And in addition to the radial drift barrier, there's also a fragmentation barrier, especially in inner disk with higher temperature. Lab experiments indicate catastrophic fragmentation happens when dust particles collide with velocities above the order of a meter per second. However, the typical relative velocities are often one order of magnitude higher than that, making dust growth limited by this solid curve. And the overall effect of these two barriers is called the meter-sized barrier. With only bottom-up growth, the dust in the entire disk fails to go beyond 10 centimeters, even after 2 million years, a significant portion of the disk lifetime. Therefore, bypassing the meter-sized barrier is the key for planetesimal formation, where top-down processes enters this game. As I mentioned, instead of gradual coagulation, they concentrate particles through dynamical processes to form dense clumps, and making planetesimal formation through gravitational collapse possible. The classical idea considered top-down concentration from the perspective of global disk scales is from the perspective of global disk scales. The idea of using pressure bumps to trap dust may date back to 1972. And yes, although theoretical models often assume disks to be simply smooth, they are not necessarily smooth, as we have already seen in these observed bright disks. And all these bright rings are currently best explained by dust trapping in pressure bumps, where planetesimal formation can be easily facilitated. And there are indeed also indirect evidence of planetesimal formation proposed. All these D-sharp rings and a few other rings seem to be marginally optical thick, as shown in this picture. Such a coincidence may be explained by a self-regulated dust removal model, where planetesimal formation takes place whenever the dust traps accumulate enough solid materials, leading to the seemingly fine-tuned optical depths. But what is responsible for these pressure bumps that trap dust? One of the popular ideas is that they are sculptured by hidden already formed planets. Quite a few kinematical planetary signatures have been found by studying the velocity deviations from the Keplerian structures of the gas disk, such as the meridional flows. However, these mechanisms in fact pose a chicken or the egg problem. On the one hand, disk substructures are desired to trap dust for the formation of planetesimals. On the other hand, how should the first generation planets form when there is no substructures? Such tension is more serious when recent disk observations found that similar substructures also exist in class 1 disk or younger objects. These two pretty examples here that shows rings and gaps from ALMA 1.3 millimeter observations are estimated to be younger than 0.5 million years. Despite the large uncertainties in their ages, the consensus is we need robust mechanisms to form the first generation planetesimals efficiently and pave the roads for subsequent planets. And my work has focused on such a mechanism to concentrate dust particles, but at very small scales compared to the disk radius. named the streaming instability. The idea is not only gas tracks particles, but particles also give feedback to the gas. In this way, particles can effectively trigger their own concentration while interacting with the gas in the disk. An often used analogy to help understanding is that birds flock together as they fly due to aerodynamic effects. And when they cluster together, they can also change the airflow around them. And similarly, dust grains in gaseous disk interact with gas by the nature of drag forces and form clumps by the streaming instability. To visualize this instability more, here we have well-mixed dust and gas in an equilibrium state. As mentioned previously, gas orbits at a subcapillarian speed, and the dust particles feel drag forces and drift inward. So whenever there is a gas pressure gradient, and now with small perturbations in dust density field, the streaming instability happens when the back reaction of the particles speeds up the gas and reduce the headwind to varying degrees and create such relative solid mass flux. Oh, sorry. So in ideal environments, the streaming instability grows on a timescale comparable to the orbital timescale, and the accumulation of solids shown in this slide will quickly become nonlinear and produce dust filaments along the azimuthal direction. So to study the streaming instability, we use the code Athena to simulate gas and particles with their mutual interactions. And because the streaming instability happens at small scales compared to the disk size, we follow the standard approach and use a local patch in the midplane of the protoplanetary disk to do our computations. This is a snapshot from one of our largest 3D simulations with the highest resolution to date. And the color on the box indicate the vertical gas motions. Red means upward and blue means downward. With ideal gas conditions, there are violent gas motions near the midplane because particles settle to the midplane under the vertical stellar gravity and form azimuthally extended filaments by the streaming instability, which consist dense concentrations in a thin layer. And those filaments are also very evident in the projected color map of the dust column density. This dust layer launches all kinds of waves in the gas that propagate to vertical boundaries. It's thus important to let such waves leave freely and not come back to affect particles again. So the choice of the vertical boundary conditions matters here. So back in 2018, we had a paper investigating the numerical robustness of the streaming instability with a suite of simulations. And in particular, we tested different vertical boundary conditions and compared our newly implemented outflow boundary conditions to the previously used periodic and the reflecting ones. And as indicated by those arrows here, they lead to different gas behaviors which further affect dust dynamics. And turbulence generated by the midplane particle-gas interactions will propagate vertically, but will come back to affect particle layer again in the first two boundary condition choice. And in outflow cases, turbulence is free to leave, so it is more realistic regarding what happens in real disks. And we found the outflow vertical boundary conditions indeed provide better numerical convergence, and especially in shorter box. And furthermore, the picture on the right shows the edge-on view of the midplane particle layer. Under different vertical boundary conditions, in the bottom panel, the outflow vertical boundary conditions allow particles settle to a thinner layer and making particle concentration relatively easier. So, what conditions are required for the streaming instability to produce strong particle clumping? Since particles trigger their own concentrations while interacting with gas, strong particle clumping requires an optimal combination of particle size, which is between millimeter to meter, and the amount of solids relative to the gas in order to have enough influence on the gas. Such a solid abundance is often evaluated using the midplane density ratio or the column density ratio, usually referred as metallicity. And in addition, suitable disk environments, like not too turbulent or outside ice lines, are preferable and will make planetesimal formation happen faster and easier. So in our most recent work, we performed a survey on these two parameters that describe solids using a suite of 2D high-resolution stratified simulations and with the previously mentioned outflow vertical boundary conditions. So as shown in the right picture, our survey systematically quantified the clumping threshold over a range of particle sizes. Each circle here represents one simulation. In those filled circles, the particle clumping is considered to be strong because the maximum particle density reaches the Ricin density, which is about 200 times the gas density. And planetesimal formation will happen if self-gravity is included. And those empty circles are cases without strong particle concentration due to low solid abundance. So these filled circles and open circles are generally separated by this green curve, which represent...
Rixin, before you go on, we have a question from Eugene Chang. So he's asking, what is your criteria for clumping versus non-clumping?
Yeah, the criteria for clumping versus non-clumping is whether in the simulation, if the maximum particle density reaches the Ricin density, and in our cases, we adopt a typical Q value of 32, which corresponds to a Ricin density of 200 times the gas density.
Thanks.
Thanks for the question. So, so here we have this green curve separating the clumping case and the non-clumping case. When we compare to previous work, our results are similar to the previous findings in Yang 2017, which focused on the smaller particles with tau s smaller than 0.01. And this is reassuring because we share similar numerical setup and overcome numerical difficulties like stiffness. But for tau s larger than 0.01, we find the required metallicity is actually subsolar metallicity, especially near tau s equals 0.3, much lower than the previous work in Korea 2015. This is because we are doing a more targeted survey with several improvements. The most significant differences is that we conduct our simulations at fixed z and at a fixed tau s, so each point here, and we run the simulation long enough, while the previous work only fixed the particle size, and they identify the critical metallicity by starting with the low metallicity and then artificially reduce the background gas density in a relatively short time scale. And besides, our simulation also has higher resolution, larger computational domains, and different vertical boundary conditions. And before moving on, I want to highlight an important implication from this low threshold at larger tau s. If young disks are populated by such particles, their interactions with gas will likely dominate the disk turbulence. And then this low threshold may indicate very efficient planetesimal formation at early disk evolution stages and provide great potential for fast formation of the first generation planets that can induce pressure bumps and create dust rings. Okay, so another remarkable feature in this figure is the sharp decrease of the critical metallicity between tau-s of 0.01 and 0.02. We have tried quite a few analyses, but currently we don't have fundamental explanations for this sharp transition. Numerically, one may guess it is the lack of resolution. However, we have chosen the case right below the clumping boundary and conduct resolution test. So this picture on the left shows the final snapshots of the edge-on dust particle layers in the radial vertical frame in our case study. And from top to bottom, the resolution increased by 2 each time. So apparently, increasing the resolution by a factor of 4 does not change the results that particle clumping did not exceed the Roche density, which is about 200. So we don't think this sharp transition is numerical. But we do notice that the midplane particle layer forms a large number of weak but very evenly spaced concentrations, and the system is sort of quiet, so these clumps never merge. So the evolution of such filaments are more obvious in these space-time plots. The picture on the left shows the evolution of the radial profile of the surface density, with x-axis being the time and the y-axis being the radial direction. So previously, we zoomed in to show the center 0.2 gas scale height. But here we are showing the entire box of 0.8 radial extent. And those filaments, they gradually drift quietly. Nothing happened. And for smaller particles like tau-s of 0.01, only at high enough metallicity, like this 2% case, do these filaments merge to produce strong clumping. And for larger particles, things get violent enough that these clumps do merge, like this one, when tau-s is 0.02. And the evenly spaced structures also fade out due to stronger particle-gas interactions, even when Z is lower. So for even larger particles, the strong clumping emerged directly from a few dominant dense filaments. So although this is only a phenomenological explanation, our results really highlight the complexity of the nonlinear dynamics of the streaming instability, which merits cautions and future studies. Okay, let's move on. Because the midplane dust-to-gas density ratio are more fundamental to the streaming instability, we decide to measure the corresponding midplane density thresholds. This picture shows a typical evolution of the dust scale height in blue and the maximum particle density in orange in one of our simulations. Since we are interested in the condition that will trigger strong particle clumping by the streaming instability, we focus our analysis and quantifications within a quasi-equilibrium period named the pre-clumping phase. It is after the initial and the transient particle sedimentation stage and before the first time that maximum particle density reaches near the Roche density, if it does. And the picture on the right shows the measured time-averaged midplane dust-to-gas density ratio thresholds for the streaming instability to produce strong clumping. Here we switch the symbols. So plus symbols means the case has strong clumping, and cross symbols means there's no clumping. And all these symbols are color-coded by their metallicity in the simulation. And here we use this purple or magenta curve to identify the density threshold. So just like the metallicity threshold, we find that the critical epsilon values, the ratio of the dust to gas density. It varies with the particle size. So it is about 0.5 for intermediate sized particles, and it jumps to about 2.5 when tau s drops or below 0.01. So previously, based on the knowledge of the linear theory, an empirical threshold of epsilon being larger than 1 is often used as the assumed condition for planetesimal formation in global disk models. So our findings demonstrate that such an empirical assumption should be taken with caution, especially for smaller particles, where a higher dust to gas ratio is required. And you can check out this website to find our fitted functions for these two thresholds, and all the simulation results are also available for interactive exploration. And feel free to play with it, it's fun. And furthermore, we also offer a generalized threshold formula considering different background drift or other sources of turbulence. Here, h eta means the particle scale height in units of the characteristic length units of the streaming instability, and a good approximation is 0.2. And h eta times pi physically denotes the particle stirring due to the streaming instability. And alpha here means the actual particle stirring due to the other sources of turbulence. So without alpha, this formula converts our critical epsilon back to the critical metallicity, which is consistent with what I just showed previously. So with this formula, one can obtain adaptive values of critical metallicity for modeling use. And for example, modeling the global dust evolution with this formula to determine when and where to convert dust mass to planetesimals. And this threshold prescription is validated by one of our other recent work, led by my collaborator Daniel Goh and Jake Simon, where we studied how the interaction between the streaming instability and intrinsic gas phase turbulence affects planetesimal formation. I saw there's a question. Oh, okay. Yeah, I'll just continue. Okay, let me first come back to the streaming instability simulations. So recall that with ideal conditions, dense particle filaments have formed in the midplane by the streaming instability. So the formation of planetesimals require particle self-gravity. If we let the simulation continue running with particle self-gravity, the dust filaments will fragment into gravitational bound clumps with radii on the order of 100 kilometers. And at this moment, hundreds of clumps have formed. Here we zoom into one typical clump where the particles are highly concentrated and bound to their self-gravity. To further diagnose the properties of these bound clumps produced in our simulations, I developed this efficient clump finding tool, Planetesimal Analyzer, simplified as Plan, which is also available at my website. So Plan can identify self-bound clumps from the 3D particle data robustly and efficiently, even for billions of particles. This figure on the right is from the snapshot in the last slide, showing the dust column density. And each clump identified by Plan is now marked by a white circle, representing the size of its heel radius. And Plan allows us to better constrain the demographics of clumps formed in our simulations and calculate their physical properties, like mass. Okay, as I have mentioned, the streaming instability operate at small scales compared to the disk size. So we simulate a local patch to properly resolve the scales needed by the streaming instability. However, turbulence in disks may come from sources that operate at much larger scales. For example, magnetohydrodynamics instabilities or self-gravitating disks themselves. So in order to study the turbulence effects, we have to mimic generic turbulence in a local patch in our simulations. And more specifically, we used forced turbulence to manually inject turbulent energy into the box by adding kinetic energy following a Kolmogorov spectrum, which can be characterized by an alpha parameter. So in this experiment, we choose parameters that are known to produce strong particle clumping and produce planetesimals. And we use the Planck code to identify these planetesimals. The picture on the right shows the main results. It is the fraction of the mass in planetesimals relative to the total dust mass as a function of the time where the self-gravity kicks in. So the control group does not have forced turbulence, and it converts dust mass to planetesimals the fastest. The blue curve have weak injected turbulence with alpha equals to 10 to the minus 4. It follows the trend of the control group with some delay, and the red curve, which with higher alpha, struggles a little bit, but then quickly picks up. However, in the case of alpha equals 10 to the minus 3, no planetesimals formed at all. So with this high resolution 3D simulation in hand, it is a great opportunity for us to test our threshold prescription. Our fitted critical midplane density ratio for tau s of 0.3 is about 0.37, and the corresponding critical metallicity for these different alpha values are listed below. So when alpha is as large as 10 to the minus 3, the required metallicity is at least 0.022, larger than the chosen physical parameter used in the simulation. And the Z critical for other alpha values are all lower than 0.02, which means the simulation should be able to produce planetesimals. So 3D planetesimal formation simulations are quite expensive. We are lucky to have this one great case to cross-validate our clumping threshold. While we keep improving our prescriptions, I encourage you to try it out in your global disk models. So you may wonder what really happened in those simulations. It is actually all about stratification. These two pictures again show the edge-on view of the midplane particle layers with and without turbulence. The x-axis is the radial direction, and the y-axis is the vertical direction. In the control group, particles are able to sediment to the midplane and increase local dust to gas density ratio, such that the streaming instability can be triggered and form dense clumps that collapse into planetesimals, like these bright dots here. However, in the right panel, strong turbulence stirs particle up and down, increase the particle scale height, and reduce the midplane dust density. And therefore, initial higher metallicity is required to increase the dust density proportionally in order to make planetesimals in this right case. So now we know that stratification plays an important role in planetesimal formation and is one of the complications one must consider when connecting the linear theory to the later nonlinear evolution. So to further highlight the complexity of the nonlinear dynamics of the streaming instability, when strong clumping happens, let me show you the diverse morphologies of the midplane particle layer in our survey simulations. So again, we are looking at the edge-on view of the particle layer. This is the final snapshots of the clumping case with tau s of 0.01. And other than a few dense filaments, there are still some remaining evenly spaced weak clumping in the end of the simulation. So for even smaller particles, for tau s equals 0.001, the particle layer somehow present fish-shaped vertical structures. And towards large sizes, the particle layer transitions to a smoother layer but feathered at the surface. And then if we increase the particle size, low density cavities starts to develop in this layer. And finally, the most favored particle size for clumping, τau equals 0.3, with a corrugated structure with significant asymmetries about a midplane. The morphologies of the particle layer reflects the complexity of the balance between the particle settling and the stirring due to the particle-gas interactions, and in this non-linear streaming instability in stratified disk models. So under such complications, can we connect the linear theory to the non-linear evolution? So let me recall that the original linear theory is derived to describe a local process without the knowledge of vertical stratification. That's why we call it unstratified linear theory. And in this work, we also made several attempts to see if we can use the growth rates predicted by the unstratified linear streaming instability to understand or estimate this clumping threshold. The picture on the left shows the expected linear growth rates as a function of particle size. And again, the symbols are color-coded by the metallicity, and plus means clumping, cross means non-clumping. And in this picture, you can see at each τau, there's no differences in the linear growth rates between the cases that produce particle clumping and the cases that don't. So in other words, those cases, although they have very similar growth rate of the linear instability, they produce either clumping or no clumping. So therefore, cautions are needed when we extrapolating predictions from unstratified linear theories to stratified disk. So to summarize my talk today, the streaming instability plus the self-gravity of particles can produce planetesimals robustly and efficiently, and it is applicable to a wide range of conditions. And here our newly found metallicity or density thresholds in stratified disk models indicate promising and efficient planetesimal formation at early disk evolution stages. And here, for the one case studied so far, planetesimal formation may be difficult under strong turbulence with alpha larger than 10 to the minus 3. And finally, the cautions are needed when applying unstratified linear theory to nonlinear stratified disk models. Thanks. I'm happy to take any questions.
All right. First, I would like to invite everyone to unmute and thank our speaker. All right.
Thank you.
If you would like to ask a question, you can use the raise hand feature under the participants tab, or you can ask a question in the chat. To start with, Eugene, would you like to unmute and ask your questions live?
Yeah, sure. Thanks, Camber. So Rixin, very nice talk. I had a couple questions. Maybe I'll just start with the second one, which is when you showed these clumping boundaries, and maybe you said this, but I just missed it. There's this sharp jump at τ(s) of 0.02. So, and it's interesting that at smaller τ(s) it actually conforms closer to the previous work. So why is there this jump? And maybe you said it, but I missed it.
Yeah. So we only have qualitative explanation is so without other turbulence, with only the turbulence from particle gas interactions, the way that smaller particles form strong particle clumping is they form such evenly spaced low amplitude filament first, and only with high metallicity those filaments can merge and produce even stronger particle clumping to exceed the Roche density. But for larger particles, they don't go through this step. strong particle clumping in the dense filament directly appeared after initial formation of the filaments. This is the qualitative differences we find. And we do and we did try to eliminate the possible numerical effect, which is the resolution. But when we test the cases that are very close to the clumping boundary with higher and higher resolution, there's still no clumping. So this is unlikely numerical. Yeah, that's just our current understanding.
Okay, thanks. My other question is, you're triggering off of the Roche density, but I wonder, which of course, if you exceed the Roche density, then you're good. You're good to go against tides. The solar tides won't rip you apart. But what about gas pressure, right? So have you checked that these clumps exceed the gene's mass? I'm not so worried about tau near 1 because you can't, because they're sufficiently decoupled that maybe gas pressure is not a serious effect. But for small tau s, I do get worried, because then the particles and the gas are better coupled and they act more as a single fluid, at least on timescales comparable to the orbit. So Roche is one criterion, fine, but it's necessary and not sufficient. You also have to beat genes. So I wonder whether you've thought about that.
That's a good point. Yeah, I guess in this subfield, most people only focus on the experiences of larger particles while doing planetesimal formation simulation, and that's why with the inertia of this mindset, we only consider the Roche density at first. So in this result, in this presentation, no, I haven't considered that.
Here's a question. When you showed the simulations where you turned on self-gravity, you got these nice, looked like bound clumps. What's the lowest tau that you went to and still got boundedness? You showed a tau of 0.3, but I wonder if you pushed even further with self-gravity.
To my knowledge and to the people I know, I think the current simulation that has self-gravity only pushes to tau s of 0.3.
I'll chime in. I understand it's easy to forget things on the spot. I had the benefit of checking while you were talking, Urshan, and there's indeed Jake's paper that we were on that went down to stopping time. Yeah, I know you remember it now. Stopping times of less than 0.01, 0.006.
Yeah, I see. Yeah,
and there it was possible to form bound planetesimals, but some more analysis of that case. That was a short letter, so I think for Eugene's good question, I think analyzing what the densities were compared to the Roche density in that simulation would be a good thing to check. Did it have to be exceeded by a large amount or not?
Okay, thanks very much.
All right, and then Vladimir Lyra has also posted a relevant paper in the chat for those who are interested. Okay, question from Everett.
Hey, Rixin, good to see you again. I was wondering with this sharp threshold in the dust to gas ratio, like what the prospects are for combining this with population synthesis to try to make predictions about the occurrence rate of planets as a function of metallicity.
Yeah, if the population synthesis start modeling from dust, from global dust in global disk models, and they have implemented conditions, so when and where to convert dust to planetesimals, then yeah, this new this new criteria will indeed, I think will indeed change some of the result, because it's compared to previous work for the dust in typical disks for the millimeter-sized dust and the centimeter-sized dust. It's easier now to form planetesimals, and if you can form planetesimals easier and earlier in the disk, we can expect first-generation planets in much younger disk, as some observation suggested. There's one thing I want to point out is, the current, our current work only consider the dominant dust size. There's no, I think there's ongoing studies trying to include distribution of dust and trying to understand what's the disk requirement if there's not only one dominant dust, but dust following some size distribution. I think in the future, we'll keep improve such criteria and keep changing the result of population synthesis, maybe. I think to.
All right. Question from Lucas.
Hi, I wanted to ask quickly that if such radiation effects, such as Poynting-Robertson drag, affects the efficiency of streaming instability at all.
If I remember correctly, I think that's more effective in like deep rig disk when the gas is gone. If those dust particles are embedded in a gas disk, I think it seems not very relevant in the protoplanetary disk stage.
Okay.
Yeah, so I find this our previous result led by Jake. So yeah, there's a planetesimal formation simulation. So with streaming instability with particle self-gravity, where the parameter of tau is 6 times 10 to minus 3. And yeah, there's still a few dozens of planetesimal formed become self-bound in the simulations.
All right. Any additional questions?
I do have one, if I may ask.
Sure.
Hey, Rixin. How are you? I was wondering, I mean, you have a slide there with a word of caution about the epsilon critical. What exactly is the caution that one should have?
You mean this one?
Yep.
Yes. So the caution I needed when one try to connect the linear theory predictions to the nonlinear dynamics of one instability. So specifically in our work, we use a numerical survey to obtain such a clumping boundary. But when we try to understand or estimate such a boundary from the perspective of the resolved linear growth rates that we can get, there's no information that we can that we can get from the linear growth rate, because for cases that produce strong clumping and cases that does not, that do not, their linear growth rate has basically no differences. So the caution is the linear growth rate has very limited predictive power on whether a particle gas system can produce strong particle clumping or not in stratified disk simulations, because the stratification was not included in the derivation initially in the linear analysis. So yeah, there are more complications to consider. So I think this also applies to the linear calculations of polydispersed streaming instability, and we will see.
So you're saying that is it the lacking of a linear theory for stratified streaming instability, or are you claiming that the clumping that you see is actually non-linear?
Yeah, it's the clumping is actually a non-linear, and there could be multi-stage process for clumping, like I have shown here. So for strong clumping that happen for very small particles, like the second panel here, initially you form this evenly spaced low amplitude filament, but when the metallicity is low, they just drift, they don't interact. But when Z becomes high, they can interact and become very dense filament, and has the potential of forming planetesimals.
Okay.
All right, question from Leo.
Hi, Eugene. Thanks for your talk. Nice to see you.
Nice to see you.
Yeah, no, I mean, I think this is maybe an interesting point. And of course, extrapolating the results from linear theory to clumping has maybe not even sense, because there's no information about nonlinear dynamics in any linear analysis, of course, by definition. So, but my question is, you show in the plot some values for the growth rate that are, it seems to be low, at least compared to the dynamical time scale. I'm wondering what is the, I mean, if also makes sense to compare such a low growth rate, or low values dynamic that you see in the simulations, in the sense that maybe there's not even possible to make a connection with the linear theory and the simulations if the linear theory predicts a growth rate that is 10 to the minus 6, 10 to the minus 7 of the dynamical time scale. I mean, it could be that whatever you are recording in your simulation has nothing to do with that instability. Would it be the case?
Yeah, yes, I see your point. So there's two things here. So here we are, sorry. In this picture, what I showed is the linear growth rate that can be resolved. So when we calculate the growth rate, so we only consider the wave numbers that can be resolved by our simulation. So if we take a look at those cases for tau s of 10 to the minus 2, those at a standard resolution, their linear growth rate are low, but despite the low growth rate, there's one case here when Z is 0.02, there's still strong particle clumping happens. And as you said, yeah, that there are indeed, it's a two-stage evolution. So first, forming evenly spaced low amplitude filaments, and then they merge to produce strong clumping. And to further investigate this issue, and really thanks for your question, we actually also calculated the linear growth rates that can be resolved by our resolution test. So you might remember that in order to check if it's a numerical effect, we did a resolution test for these cases near the clumping boundary. We increased the resolution up to by up to 4 times. And when the resolution increase, as shown in this picture, these 2 dots here, the simulation should be able to resolve much more faster linear growth rate, which is actually comparable to the orbital timescale because it's near 10 to the minus 1. But still, there's no growth in those resolution tests. So, so yeah, what you said is right, but still, cautions needed.
So, thank you. I mean, thanks for remarking that that's sort of the glory that are in agreement with the resolution that you have. So maybe it would be useful also because the streaming instability, the glow rate will saturate with as you go to a smaller scales. At some point, it will reach a maximum value. So it will be interesting to see what will be the expected value, and what will be the resolution required to reach that glow rate. I mean, for all these points, I guessing what you say is that the one that has 10 to minus 1 is that exactly like if you go to the green, like top, 10 to the 2 or larger than 10 to the 2 vertical wave number here in this plot. At that scale, the growth rate will start to converge and to reach the maximum possible value. So,
so I would say that so here this is the growth rate color map as a function of wave number in the x radial direction and a wave number in a vertical direction, and this one tau s equals 10 to minus 2 and the metallicity equals 1.33% is the case that we did the resolution test. So we are finding the growth rate that we can resolve within this rectangular. So the dash curve means the dash curve means the requirements by the numerical resolution, and this solid curve means the requirements by the vertical particle layer, the vertical extent of the particle layer. So when we increase the resolution by 4, this black dot is the fastest growth rate that we can resolve, and I think it's pretty it's pretty fast already, and it's only the weight of the
that color scale it seems to be fast.
So yeah, I think it should be able to resolve if there's
Okay, thank you.
Thanks for the question. Let me show you more.
All right. We are at our time, so we're going to stop there. Thank you all so much for attending the Origin Seminar this semester. We plan to continue hosting these over Zoom starting again in January. Hope to see you then. Until then, everybody please take care. Bye.
Thanks everyone for coming.
Bye.
Thanks.
Thank you, Rixin, for your talk.
Who is recording?